All right, hello everyone, and in this video we are looking at certain concepts that will be relevant throughout the entire curriculum, but certain things that you might want to know at the outset so that when these are applied later on in the other chapters as applications or tools used in order to improve your understanding, you are not at sea. Okay, so starting off with it, you might have encountered this as the first chapter in your textbooks or the first thing that you started off with in school. um, Ideas regarding measurements, ideas regarding errors, uncertainties, and basically how to go about understanding the process of measurement, so to speak, right? So first things first, before we start our journey into the realm of measurements, let us first set a few definitions, right? Or for that matter, let us look at a few key uh, concepts that we encounter every now and then. So the first concept being the system. Okay? What is a system, right? Because you've heard this being said time and again, right? And you will be hearing it. I'll be using it every then and now. That we are discussing about this system, that system. What comprises a system in a physical measurement scenario? What comprises a system? Okay, so it's very important to note an organized set of interdependent entities working together to form a more complex one. So let's say, for instance, F equals to ma, force equals to mass times acceleration, right? So it actually can be thought of as uh, a correlation, okay, between mass and acceleration to produce force on a given system, right? Like two objects colliding with each other, right? They both comprise a system. Both the objects are independent entities, right? But as soon as they start interacting, they are interdependent. So it's the interdependence that we are studying here, and the understanding of the interdependence is built by the correlation that we are looking at. And in order to cement the correlation, in order to establish the correlations on more solid footing, we need experimentation, right? So establish relationships to find the variables, right? So because you might be knowing about this when you are forming your research questions for your investigations, right? You are asked to try and figure out the variables between which you are looking to build a connection, right? So experimenting on systems is to the goal is to establish relationships between the interdependent entities and understand the dynamic equilibrium that exists. Okay, so the equilibrium that they're talking about is not a static one; it is subject to change, right? It's subject to change because the variables themselves can change in terms of their values, right? So the goal is to form a mathematical relationship between variables that represent the changes taking place within a system so that we can understand what are the changes that are taking place within the system and how these variables are related in the context of those changes. So if an object starts moving faster, then we measure its acceleration, right? And we have the mass. So then we can show that the mass times acceleration gives me the force. And every time the acceleration changes, there is a change in the force. And that's how we arrive at the correlation between force and acceleration for a given system, right? And the variables themselves start defining the system. Another example might be, say, a container filled with gas, right? So we say that this gas is at this certain value of pressure and it's enclosed within a certain volume and at a certain temperature. So the pressure, volume, temperature, these interdependent entities are now working together to form the system that is known as an enclosed gas to us. So every system that we see will be defined by these variables, and our goal in terms of experimentation would be to cement a mathematical relationship between these variables that go on to define the system. All right. Now, in terms of variables, of course, I'm pretty sure all of you have a bit of an idea regarding these variables. Like the first thing that you learn when you're drawing a graph is that you have y and you have an x, right? The axes. So you're generally told that you plot the independent variable on the x and the dependent variable on the y. It's subject to change, but that's a convention we follow. It makes it easier for us to understand which is the variable that you are trying to vary during the experiment, and which is the one that is changing on account of the change in the other. So the independent is the variable that you change during the experiment, right? It's the interchangeable, interdependent, one of the interdependent quantities that you are investigating. And the dependent is the interdependent entity that is dependent on the change in the independent, and this will eventually lead us to a relationship between the two of them. Okay, so remember, this is the key to forming a good research question. Independent and dependent variables are physically measurement observable or physically measurable quantities. All right. So when I say physically measurable or physical observable quantities, then for example, you don't take size as a physical measurable quantity. Though colloquially, size can imply a variety of things. It can imply volume. It can imply surface area, right? It can imply length in terms of strings and rods, stuff like that, right? So no vague variables are allowed in the physical domain. Any physical entity that you are taking as either independent or dependent must be physically measurable. All right. So no talk of size or any vague terms that you might use colloquially to explain your hypotheses, but in a research question, it needs to be an independent and dependent variable that are physically measurable or physically observable. Then comes the third. It's also important. It's kind of quite important in the context of the independent and the dependent, because there might be an equation where x, y, and z are related. So let's say z equals to x into y. All right. So this is the equation, and I want to observe the change in z on account of x. So in my investigation, y cannot play a role. So y will become a control. All right. Similarly, if I do not want x to play a role and want to discern a relationship between z and y, then z becomes dependent and y becomes independent, with x becoming the control. Similarly, of course, if z remains constant, I can find out a relationship between x and y. So these are certain things that I will not be repeating again, but I would like you to keep a clear head and try and understand where I'm coming from when I say this, when I use these kind of arguments to try and look at the relationships, because we will not be doing experiments per se, but it's equally important for you to look at a given equation and be able to figure out what kind of a relationship exists between them. So z equals to x into y, right? So if I take z and x, then z and x are directly proportional if y is constant. Similarly, z and y are also directly proportional if x is constant, but x and y are not directly proportional if z is constant, because x is equals to z by y. So x and y are in fact inversely proportional. X increases, y decreases, and vice versa, with z remaining constant. So these are a few things that come to mind that kind of are used time and again in our discussions. All right. to illustrate the importance of relationships between variables. And it also helps us visualize what kind of graphical relationship the variables themselves might have between themselves. So independent, dependent, control, three kinds of variables that are of paramount importance when we are looking at a system and trying to do some experimentation in order to build relationships between these interdependent variables so that the changes within the system can be understood better. Now, carrying on in that same vein, while you are measuring, of course, you'll need measuring instruments. It's a brilliant observation. But that is not all. Every measuring instrument comes with its own set of limitations. Okay, so, and these limitations form a very, very important part in documentation of the experimental data in physics. Okay, so which is why, I mean, like when you are looking at a huge breakthrough in the sciences, right? When they say that, okay, we have discovered something that was theoretically predicted a long time back. That took time because the physical measurements required instruments that were more sophisticated, right? In general terms. So the sophistication in instruments was required because otherwise those measurements would not have been possible, because there would have been too many errors, too many mistakes in those readings had those developments that we are talking about right now not been made, right? So let us look at these errors, these limitations, right? Upon which, sadly speaking, even though we are trying our level best to, upon which but help doesn't seem to be at hand. And why that is so, we will learn later in when we do quantum mechanics, in fact, wherein this line actually becomes a sad reality, and we will see that this cannot entirely be negated. No matter how hard we try to control things, some level of experimental error is unavoidable. Okay? And no measuring instrument is perfect. So, no matter how sophisticated the instruments get, and no matter how close to the actual value we get while making those measurements using those instruments, no measuring instrument can give us 100% accurate result. All right? Now, there are two quantities that you would be encountering every now and then. One of them, it's called an error, and the other, it's called an uncertainty. Okay? Now, it's quite common amongst people to treat both of them as the same because, I mean, linguistically speaking, in the context of experiments, if you make an error, then the certainty with which you can claim that your result is reliable goes down. And if your result is uncertain, then it kind of implies that there was an error that might have crept up in either the instrument or the method followed by you. So it's pretty common to treat both of them as one and uh, exactly the same, but they're not, of course. The build-up was to that. So wherein lies the difference between errors and uncertainties? Now, this I find incredibly helpful. An error is the difference between the measured value and the expected value of a given variable. Like say, acceleration due to gravity on Earth, g, is 9.81 meter per second squared. We are all aware of that. So that can be taken as the holy grail. So that is the most accurate value of acceleration due to gravity that we can get up to 2 decimals, right? Now let's say your experimental value of g that you calculate gives you 9.02 meters per second squared. All right. So the error is 0. Point, sorry, right? 0.79 meter per second square is the measured value, difference between the measured value and the expected value. So the expected value is this, and the measured value came to be that. All right. Now, what about uncertainty? Okay. Now, the uncertainty is a way of expressing or summarizing the error. Now, this is not really very helpful. Okay, it's still vague, though it tries to move away from saying what an error is and what an uncertainty is. Okay, the uncertainty I think is way better explained in terms of the limitations of measuring instruments. Okay, in most instruments, if we come to the last point, the limitation of measuring physical quantities by means of instruments is fixed by the least count of the instrument. So this is what fixes the sophistication, the level of precision with which the instrument would be able to give me measured values. So least count, the smallest division on the scale of the instrument. So this gives me uncertainty. Now, of course, as you can see, this uncertainty, this limitation in measurement might have played a role in this value, the experimental value of G becoming 9.02 rather than 9.81. So, like I mentioned, the presence of uncertainties kind of implies or necessitates the presence of an error. And similarly, if there is an error, then of course there have experimental uncertainties do remain, but the presence of uncertainty is as unavoidable as the presence of an error. All right, because of the thing that we started off with, the limitations in measuring instruments. Okay, so you will never have an experimental result wherein you uh, get the experimental value exactly equal to the expected value, right? Primarily because your measurements themselves are uncertain up to the degree of what is fixed by the least count of the instrument. Which leads us to another discussion, a discussion on precision and accuracy. Now again, much like errors and uncertainties, precision and accuracy have for long been considered one and the same. But they are not. So accuracy is how close a measured value is to its true or accepted value. Which means in the previous slide, which we saw, if this delta of measurement of G between the theoretical value and the expected value were way smaller, then we would say that the measurements were accurate. So reduction in the error value leads to greater accuracy. So measurement error reveals the amount of accuracy. All right. Next comes precision. Precision is a degree of consistency and arrangement among independent measurements of the same quantity. Like if I measure length of a given object using a meter rule, okay, and I express all my readings in, say, centimeters, right? We all know the meter rule ranges from 1 to 100 centimeter. Sorry, 0 to 100 centimeters. All right. And the least count is 1 millimeter or 0.1 centimeters, right? Which kind of implies why between 1 and 2 you have 10 readings. Each small division accounts for 0.1 centimeters being covered. So the precision of this instrument is fixed at 1 dp if I am using centimeters as my unit of measurement. So all my measurements will only have 1 dp and 1 dp only. It cannot go beyond if I use a meter rule, right? So some technical terms again, 0 to 100 centimeter is called the range of the instrument, unless you're familiar with it, okay? And least count is 1 millimeter or 0.1 centimeters. So all readings need to stay pegged at 1 dp and they cannot go beyond that. So precision is a pointer towards the consistency of the data. So if I have a data that is less than 1 dp, which means there are no decimal places, then I need to write, say I get 2 centimeter as my reading, then my representation would actually be 2.0 centimeter to denote the fact that there is a dp which was not required because the scale was fixed at 2 centimeters in order to make it consistent. So increase in the precision, right, improves the number of decimal places. Number one, you can think about it that way, right? If I were to use a screw gauge, the least count is 0.01 millimeters, right? So it becomes more precise. The degree of consistency needs to be higher because there are more number of decimal places being considered. So we are actually looking at a kind of precision which is overriding the precision due to another instrument which has a greater least count. So if I were to measure the width of a human hair, I would not be using a meter rule because the meter rule's least count is 1 millimeter, whereas the width of a human hair itself is far, far less than a millimeter. So you can't use an instrument which has a very high least count to measure something whose dimensions are smaller than the least count of the instrument. So it's not consistent with the precision of the instrument. The precision required is far greater, right? So an instrument therefore can be precise, but whether it's accurate or not depends on other factors. There might be errors present within the instrument because least count of the instrument will not change, but there might be some error in the functioning of the instrument, right? And because of that, the readings might change and that would affect the accuracy, but it would not affect the precision. All right. So with this, we come to the end of this video. More discussion on this later.